Welcome to Catastrophic Science, where we show new findings that have resulted from catastrophes. Results that can save lives in the future. The 2003 Canberra bushfires were some of the worst in its history. Almost 70% of its surrounding pastures, forests and nature parks was severely damaged. Several people died. More than 490 were injured. And firefighters at a loss to explain the unfamiliar pattern of the spread. Normally bushfires spread with the wind, but in a number of places these fires actually spread across the wind. One even spawned a fire tornado, the first one ever recorded. Luckily, these fires were extremely well documented, so scientists from UNSW Australia began researching with firefighters to understand what had happened. So Jason, can you explain how this fire differed from normal?
Usually the most intense fire behaviour is associated with fires spreading upslope with the wind. But what we found is that under extreme conditions, you can actually get the most intense fire behaviour in association with lee slopes, where the fire spreads across the slope. So VLS stands for vorticity-driven lateral spread.
Okay.
And so that's what we've called the phenomenon, because it basically occurs due to the fact that the fire will interact with the winds going over the lee slope and create whirlwinds, which is vorticity, and that's what drives the fire sideways.
Yep.
It's also associated with a lot of spotting, which is when you actually get little bits of burning embers and so on, which are blown downwind to start new spot fires. For this particular effect to occur, we need to be on a lee-facing slope to begin with. We need it to be fairly steep, so over about 25 degrees. And we need fairly strong winds over about 20 kilometres per hour. We're able to replicate the effect in wind tunnels, and it was quite satisfying from my point of view to see the surprise on my Portuguese colleagues' face when they saw the fire go sideways. They weren't expecting that at all, and we're also able to replicate the effect in these computer simulations. Traditional models really treat a fire on its own without considering its effect on the atmosphere. So what we found with these extreme fire cases is that it's really the interaction between the fire and the atmosphere, so the fire affecting the atmosphere and then the atmosphere in turn affecting the fire, which drives these effects.
This idea of the atmosphere and fire interacting, was that a major contributor to the fire tornado occurring?
Yeah, definitely. The interaction between the fire and the atmosphere actually creates large areas of fire, so what we call deep flaming.
Okay.
These areas release large amounts of heat and moisture, which then interact with the atmosphere to produce thunderstorms.
Yes.
And it's these thunderstorms which then are able to produce tornadoes. So what we found in the case of the Canberra fire is that the fire created a supercell thunderstorm. The supercell thunderstorm then created a tornado, which we estimated to be somewhere between the F2 to F3 category, which means that they had winds in excess of about 250 kilometres per hour.
That's incredibly powerful as an actual storm itself.
Yeah, I mean, it did a lot of damage in its own right. This was the first documented genuine fire tornado. I mean, there's been a lot of people who have seen what are called fire whirls. So these are sort of spiralling columns of fire which are attached to the ground.
Okay.
A genuine tornado is a different thing. It's actually attached to the base of a thunderstorm.
What's next for your research in this field?
To get a better understanding of the actual physical mechanisms driving these effects, and through that we're able to provide better guidelines for operational firefighting and community safety.
These findings are absolutely critical, and they're vital for us to be able to effectively manage these fires and overall keep our people safe.
Fires don't read manuals or follow what the textbook says they should do. They can behave very erratic depending on weather conditions. They can create their own climate and localised conditions, and that depends on terrain, wind behaviour, temperature, the whole lot at the time. So any research towards that would be of great assistance.